So welcome guys to our radiation heat transfer learning journal, and we were talking about the radiation transport equation or radiation transfer equation. We have just derived a form of the radiation transfer equation as shown here. So as you can see, the radiation the change in the radiation going through a system, it's basically due to the what do you call that? The emission term is contributed to by the in-scattering term, and of course the extinction term here, which is a combination of outscattering and absorption. So of course the reason why we want to derive anything in the first place is we need to solve problems with this thing. Alright, we want to solve problems with the radiation transport equation. So yeah, so for example, the goal at the end of the day is well, again, we have let's say two plates or two surfaces instead of plates. It could be a gray surface, and then all this middle stuff is the participating media. Alright, participating media, and question is how do we solve this equation, right, of heat transfer, right? Heat transfer between, let's say, the plate number 1 and plate number 2. Or even better, there are cases where you have participating media transferring heat to the surfaces. For example, let's say you have a pipe, alright, a pipe that's carrying some combustion gas, alright. This pipe carrying some combustion gas. So let's say you have a combustion gas, so a burning mixture of, let's say, methane plus air. Alright, methane plus air, and then you have water and carbon dioxide going through this pipe, and then it's very hot. This can be easily maybe 1500 Kelvin or higher. So this is an estimate of the temperature that's getting from the gas. So it's flowing through this pipe, perhaps it's some heat exchanger or something. So there are a few processes going on here. There's convection, there's conduction, and now obviously, because the temperature is so high, there's radiation. Now radiation is not as important in the lower temperature ranges, for example 300 Kelvin. It's not as important because radiation is determined by sigma T to the 4th. So temperature is a very important factor in radiation heat transfer. So usually only in high temperatures, such as 1500 K, does radiation become more of a problem. Maybe 1000 K to 1500 K upwards, you have to start considering radiation as well. So these are some of the reasons why we wanted to start with our radiation transfer equation. And as you can see, it's pretty complicated, and if you want to solve it analytically, we'll have to make many simplifications. So to solve analytically, we need to make many simplifications, because as you can see, this scattering term here kind of makes it an integral differential equation. So differential because there's this dids here, the integral part is here. Scattering just messes everything up. It makes it very complicated to solve. So to solve analytically, it's not very practically useful, but we want to solve it. at least computationally. And there are a few methods to do that. Hopefully we can go through some of them. There are the discrete ordinate, spherical harmonics, simplified spherical harmonics. These are very interesting numerical methods. Okay, so okay, let's put this in. I want the picture of this. Right, the picture of this in. At least give us an idea of what we are trying to do. So the numerical methods, we want to use something called spherical harmonics or discrete ordinates, or even maybe simplified spherical harmonics. There are lots of methods there. Okay, so yeah, even with computers, it's going to be pretty complicated to solve. So anyway, the baseline is of course to start with analytical solving. So we want to start with analytical solutions for extremely simple cases. Alright, so analytical solutions for extremely simple cases, just to get some kind of grounding for ourselves. Of course, even in analytical solutions, there are also approximations, but we can cover that later on as well. And these are just for some background knowledge, so that when we run into numerical methods, it will be we have some grounding. We know what we are doing. We know what all these letters and symbols mean. All right. So first thing, we want to start with analytical solution. So we start with this, and what do we want to find out? We want to find at least some heat transfer rate. So stuff like heat flux, divergence of heat flux. These are important quantities to find out. So this is our kind of end of the objective of this, and of course we'll want to find, let's say for a simple case as well, maybe between two infinite parallel plates or even spheres. So these are usually the textbook kind of scenarios that we are dealing with. So firstly, we want to simplify the radiation transfer equation, RTE. So two ways. There are two things we want to do. We want to get rid of time dependence, and secondly, I'll get to this shortly. You're like wondering, where's this time dependence you're talking about? Okay, I'll show that shortly. And the second thing is to include optical thickness. Okay, so optical thickness is that tau, the tau lambda we are talking about earlier. So at least these two will help to simplify our radiation transport equations to so it's slightly more palatable. All right. So where is this time dependence coming from? So in the equation itself, it's pretty hard to see, but let's do this, or rather, let's use the same diagram as before. Okay, you have some ds, all right, some length ds, right, and you have some dA here, and as usual we'll have some radiation that's transferred from here, I lambda, and I gotta put my lambdas properly, I lambda, and this is in s hat I, and this is evaluated at s. This is our classic radiation problem. S at I, evaluated at S plus ds. Okay, this is what we are normally used to. Okay, However, we got to note something, right? It takes a finite amount of time for this radiation to travel from here, or from S to S plus ds. So there is a time factor as well. So at time t, if you were to include time, I mean this is a physical world after all, at time t, this radiation is at here, is at S. Then the radiation, this intensity or this beam of radiation, it takes a time dt to travel through ds to appear on the other side. So I'm going to type out because it's really long. Let's use a font size of 48. Okay, so radiation takes, or the beam of radiation takes dt to travel through the medium of length ds. And that makes sense, doesn't it? I mean, maybe I'll use blue color instead. So, I mean, if the radiation was, if let's say this, if this was a function of time, okay, if this radiation was a function of time, yeah, then we'll have kind of an issue, because yeah, if it takes very long to travel through this system, okay, if it takes very long to travel through this system, okay, let's say it takes 10 hours to travel through this system, okay, then what will happen? Okay, so let's say this radiation coming in as a sinusoidal input, okay, it's going to come in here. If it takes 10 hours to travel through the system, okay, so on the other side, before 10 hours, t less than 10 hours, if it, this is just an example, then here the I lambda S plus ds equals to 0, right? But the I lambda here at S is the sinusoidal function, right? This is the sine function. Okay, so in fact it takes at least, if the radiation travels very long through the system, it takes at least 10 hours. 10 hour needed for steady state, right? If it takes 10 hours to travel through this system, it needs like 10 hours for this thing to settle at steady state, right? So if let's say you suddenly change it to a square, a sawtooth or a square wave, you change this radiation into a square wave, it takes 10 hours for the response, the signal, to travel from here to here. However, if let's say your signal, I mean, it takes literally like a few femtoseconds to travel through this system, the steady state kind of is achieved. Yeah, the steady state is kind of achieved almost instantly. So steady state is achieved, okay, quickly because of low transit time. Right? It is achieved quickly due to low transit time. So how do we put all of this into a mathematical statement and say that, okay, the transit time is low enough so that we don't really have to care about, you know, the time lag it takes for the radiation to travel from here to here, because that may play a role as well in certain cases. So this is what we are going to do. So let's find time dependence. So first thing first, where it appears mathematically, it's in this term here, the dids term. All right. So how do we extract the time dependence out? So normally what people do, we'll do this partial derivative thing, right? Partial I partial t dt plus partial I partial s ds, right? Partial I partial t dt, partial I partial s ds. So to convert it into this, we just divide throughout by ds. ds. So remember, this left term represents the time lag I was talking about just now. If the transit time it takes for the radiation to move through this system, it takes very long. If the transit time is short, we don't really have to care. So let's divide by ds throughout. And here, this ds will just disappear. Now, dids equals to all of this times this plus this. Alright, what is this term here? What is dt ds? Okay, well, that's pretty simple because we found out what dt ds was just now. Okay, I'm gonna wait for it to paste properly. So remember, we're saying the beam of radiation takes the time dt to travel through the medium of length ds. So okay, the beam of radiation takes time dt to travel distance ds. So this is the speed of the radiation, or rather 1 over the speed. ds dt is the speed of the radiation. So what is the speed of radiation? It is the speed of light in that medium. Okay, so, and this is equals to C naught divided by the refractive index, if you want to be so precise. Okay, so ds equal dt ds, all right, that is equals to n divided by C naught, or the other way to write it is just 1 over C. Yeah, and we know that C is an unusually big number, okay, by human standards anyway. C equals to 2.998 times 10 to the power of 8 meters per second, right? So okay, we notice that this time dependence is severely, like, you know, divided by C. All right, so this thing will have to move pretty fast. I mean, the time dependence of the radiation input signal, or the input radiation, would have to move really fast and be comparable to the speed of light. Or at least C naught should be this. I mean, yeah, C naught should be this, and even for refractive index, refractive index of 1.5, I mean, the speed of light is still dramatically very fast, right? Okay, so the speed of light is pretty fast in that material. Yeah, so if you take a look at the equation here, yeah, this is equation 1020. This is exactly the same thing they're talking about here, except now it's put in a wave number format. Okay, it's kind of redundant. I'm just repeating what I've been saying. So, but yeah. So usually this the t term is really much smaller than c for that system, unless for a few special cases where maybe you talk about the I don't know, electrical fiber optics or lasers. You have this term popping back in. So except for a few special cases, let's see whether it has this case. What is the simplification? Yeah, so over the last few years, primarily due to the development of short pulse lasers with pulse durations in the picosecond and femtosecond range, transient radiation phenomena has been becoming of increasing importance. So these are lasers, short pulse lasers with picosecond or femtosecond transients. So these are having very fast DIDT that you can't ignore it anymore. Otherwise, it's however this signal changes, C is so big that it kind of just disappears. It's very negligible. So for the most part, unless we are dealing with extremely fast laser pulses or other special cases, we can ignore the time dependence. So effectively, the IDS equals, it will just become a function of space, right? So even if you have transient phenomena, let's say I was talking about earlier, where we have this combustion gases going through, maybe the temperature varies from time to time, but the speed of light in the medium is so fast that the radiation field is reaches steady state pretty quickly, within a matter of a few 10 to the minus 6 or 8 seconds. Very fast. Okay, so the radiation field is set up pretty quickly because the speed of light is very fast, so we don't really need to consider the time lag of that signal, which is good news. Then we can get rid of this time dependence term. So therefore, at least that part is being taken out. Without time dependence, we get this form of the radiation transport equation. Next thing, of course, is to include this optical thickness, right? So probably that will be a subject for the next video, but let me just copy and paste what the definition of optical thickness is here. Okay, for optical thickness, tau lambda is this, and I'm going to stop the video here, and I'll see you guys next time. Thanks for watching with me. Thanks for watching this video, Radiation Learning Journal. I'll see you guys next time. Bye bye.